Okay, students. So we are going to design a underground water tank. Underground water tank rectangular shape. So water tank are used for the store water to tide over daily require of water by localities, industry, campuses, towns, and city. So water tank are used for the store the water. Okay, and we have a shape like circular shape, square tank, rectangular tank, infantine tank, polygon tank, spherical tank, and conical tank. So in this chapter, we are going to learn circular tank, square tank, okay, then instant tank. Okay, so shall we start? So capacity of water maybe may be formed by considering the number of persons using the tank. Capacity of water tank you can find out easily by considering the number of persons using the tank. If you have a how you going to build that water tank on a one bungalow, so will you find out how many person will live in this area. Okay, in this bungalow. So usually estimate of use of 135 liter per capita per day. 135 liter per capita per day water is required. Okay, for one person, for one person for a one day. And if example we have a five person in a one family, five person in a one family, at that time 135 liter, five person, and 2 days. I am going to design a water tank for the 2 day store water, 2 days. Okay, so 135 liter, 5%, 2 days, and 1350 liter of water required to be stored in the water tank. So therefore I am going to design a water tank for a 1500 liter capacity will be sufficient for the store of water for the 5 person for 2 days. Okay, this type we can find out capacity of water tank. Then one second one is design requirements. So for the design a water tank we have a IS code IS 3370. We have a 4 part here, 1 2 3 and 4. All the 4 parts are used for the design of water tank as well as storage of liquids, so in this case IS 3370, this IS code, this Indian standard code is used for the design of concrete structure for the storage of liquids. Okay, special consideration. Okay, so for the design of water tank we have a two consideration here. First, the concrete should be impervious, means no leakage in there, and no cracking in the concrete due to loads. No cracking of the concrete due to load. Okay, this two consideration is required. Here is a impervious, means your water will not flow out from the concrete. Okay, so these two considerations. And right now we have a minimum reinforcement. Here minimum reinforcement is depend on the thickness of wall. Minimum reinforcement requirements is depend on the thickness of wall. So minimum reinforcement up to 100 mm thick, means your water tank wall is not more than 100 mm. That time area minimum reinforcement is 0.3% of the concrete section. Okay, 0.3% of the concrete section. Okay, same thing here between 100 mm and 450, means first is 100 mm. Okay, if limited is not more than 100 mm, thickness is not more than 100 mm, at that time percentage of steel is 0.3%. Okay, first consideration. Second, 100 mm and 450 mm. In between this 100 mm and 450 mm, in between this percentage of steel required is 0.3 to 0.2 percentage. Look at here, 0.3 for the 100 mm thick and 0.2 for the 450 mm thick. Okay, means simple logic here. If a thickness of water is in between 200 mm, in 200 mm, that time percentage of steel is 0.2 percentage or 0.2 percentage. In between these two means it will be 0.24 percentage, 0.21 percentage, okay, 0.28 percentage. Okay, so in between the thickness of water tank wall is 100 mm to 450 mm. At that time we require PT in between 0.3 0.2. Here is calculation. So if 100 mm thickness wall, percentage of steel is 0.3 and 450 mm thickness wall, percentage is 0.2. Okay, here is the equation. PT is equal to 0.3 minus 0.1 into T minus 100 divided by 450 minus 100. These are the equation to find out PT. For what? In between 100 and 250 mm. Thickness in between 100 and 450 mm. Okay. Let's hope. I will explain it. This equation is not, remember, is good. I will explain by one mathematical step. Okay. Look at here. 100 mm, 450 mm, 0.3, 0.2. Okay. And my wall thickness is 200 mm. I don't like to remember this equation. I don't like it. I go the simple mathematical step. So what we do? T is equal to 200 mm. So thickness is 200 mm. First of all, I have to find out the difference between these two. Difference. I am going to find out difference between these two, thickness and percentage. So thickness difference is 350 mm. Okay. Thickness difference is 350 mm. So I can say a 350 mm thickness, percentage of steel difference is 0.1 percentage. If difference between thickness is 350 mm, then percentage of steel is 0.1 percentage. Difference, both difference, and right now 100 to 200 mm difference. So yeah, I can say 100 mm difference. What is the difference between the percentage? What will the difference between the percentage? Simple mathematical step. You can find out difference here. You can find out difference here. After find out difference, 0.3 minus difference, 0.3 minus difference, you can find out PT. You can find out PT easily. So simple step is here. Okay. Now minimum reinforcement greater than 450 mm. Minimum reinforcement for more than 450 mm. Okay. For the more than 450 mm, minimum reinforcement required is 0.2 percentage. Minimum reinforcement required is 0.2 percentage for the thickness more than 450 mm. So what you have to remember? You just remember two value. 100 mm, second 450 mm. Okay. In between two value, 100 mm 0.3 percentage, 450 0.2 percentage. So if I say minimum, if your thickness is less than 100, thickness is less than 100, value is 0.3. If your thickness is more than 450, volume PT is 0.2. And your value in between these two, 100 and 450, 100 and 450, your value in between this. Simple logic. Okay. So you just have to remember these two values. Okay, and right now we have one note here. A minimum reinforcement specified above may be decreased by 20% in case of high yield strained deformed bar. Specified above may be decreased by 20 degree in a case of high yield strained deformed bar. So this percentage 0.3 and 0.2 is for mild steel. 0.3 and 0.2, this percentage for the mild steel. but I am going to design the reinforcement for the HYSD bar, high yield strain deform bar. At that time, my percentage value is decreased by 20%. Is decreased by 20%. So I am saying that there is a 100 mm thickness wall. Then I think this wall. A 0.3% PT is required, minimum required. This for the mild steel. But I am going to use HYSD bar. So what the value is per PT value is changed. How much change? 0.3 into 0.2. 20%. So 0.3 minus 0.06. So 0.24. Okay. So for the HYSD bar, PT value is 0.24 and for the mild steel, PT value is 0.3. Okay. Right now we have a different joints in the tank. Joints are too important for the tanks. Okay. So first joint is movement joint, second is construction joint, and third one is temporary open joint. Okay. First is movement joint. So movement joint. Movement joint, why we require movement joint? Movement joint we require to maintain the water tightness. Maintain the water tightness while accommodating relative movement between the sides of the joints. Okay. If I say here is a rectangular water tank, okay, here is a circular water tank. Which one is give the better result? Obviously circular. Okay, circular water tank give you a better result. But in the rectangular tank, your joint will be filled. Joint will be filled. At that time, we need a movement joint. We need some expansion and as well as contraction. Expansion as well as contraction, but never create a crack here. Okay, so this type of joint is called a movement joint, which allow to expand the concrete as well as contract the concrete. Okay. Movement joints, we have three types of movement joint. One is contraction joint, expansion joint, and sliding joint. First, let's start. A construction joint is a typical movement joint which accommodates contraction of concrete. The joint may be either complete contraction joint or partial contraction joint. Okay. In the case of complete contraction joint, both concrete and reinforced steel are interpreted. But in the case of partial construction joint, only concrete is interpreted and reinforcement still running through. Let's check if I have a figure. Okay, yeah. Okay, here is a contraction joint. At a contraction joint, here first is complete contraction joint. Complete contraction means here is a joint is here. Is a discontinuity in the concrete. Is a discontinuity in the concrete as well as in the bar. As well as in the bar. It's called a complete contraction joint. But in a partial contraction joint, there is a plate is here. Okay. And joint sealing compound we feed, but a reinforcement is all along. Only concrete is discontinued. Only concrete is discontinued, but a reinforcement is continuous. So this type of called a partially contraction joint. Okay. In the complete contraction joint, both concrete and steel, both are discontinued. But in the partial contraction joint, only concrete are discontinued, but reinforcement are still connected, is continuing. Okay. Expansion joint. So same thing is a contraction expansion. Expansion is about 30 meters to provide without. Okay, 30 mm for the provide with or without water barriers and portion of joint is speed up with a joint filler, filled up with a joint filler and water bars. And water bars. Let's check. Here is a figure. Yeah. So this point is used for the give the concrete to the expansion. Okay, space for the expansion. Okay, this initial gap, this is minimum 30 mm, not more, and this is filled by joint filler or water bars. Water bar is nothing, just a simple bar is here, but joint filler and water bar, these are filled. Okay, and this is compaction and sometimes expansion. So this joint is give the space for the expansion of concrete. Okay, slim is sliding joint. Sliding joint is look like this, at a base and a wall, at a base and a wall junction. At this time we call the sliding joint. What happens in sliding joint? Your wall will be moved both direction by sliding joint. Not a larger movement, but a sliding movement. Okay. By this joint, you cannot see a bending moment. You cannot see a bending moment in a wall. Remember, one thing I will explain it. Okay, so look at here. First base is here and here is a wall. So it's a free to move. Okay, sliding, free to move. So at the sliding joint, when the water pressure is applied on the wall, your wall will be moved. Simply its wall will be moved. Okay, and if I say it's the joint here, it's a rigid joint. Okay, no sliding joint applied at the base, it's applied a rigid joint. At that time wall will not move but is bent by water pressure. But while we provide a sliding joint, your wall will be moved and this will not resist a bending moment. So no required of bending moment or reinforcement. When we apply a sliding joint, we need not require a bending moment reinforcement, because the wall slightly move and there is no cantilever portion effect are there. No cantilever portion, no cantilever effect, nothing are there. So when you apply a sliding joint, no cantilever movement. Okay, construction joint, simple is we provide a temporary joint. We will not construct a fully a wall in a one filling. Okay, oh, I can say there is a 4-meter wall. Okay, 4-meter height wall. At a 4-meter height wall, we will construct in the parts and parts. Okay, so for the parts we are use this type of joint as this called a construction joint. Temporary open joint. Look at here temporary open joint here. Simple. It open for the some work. Okay, this open for the some temporary work and then after is filled by a concrete or a brick or any joint sealing compound. It just open for some finishing work. Okay, right now design constant, we have some design constant. First, neutral axis. Neutral axis x balance. Neutral axis x balance equation is m sigma cbc divided by m sigma cbc plus sigma st into d is equal to kd. K is a neutral axis constant. Here is a final equation and here is k is a neutral axis constant. So k is equal to m sigma cbc divided by m sigma cbc plus sigma st. Okay, so sigma cbc is a permissible stress in a concrete, in a bending, in a compression. Permissible stresses in a concrete, in a bending, in a compression. Okay, and next one, permissible stresses in a steel, in a tension. Okay, sigma st. M is equal to modular ratio. So modular ratio equation 280 divided by 3 sigma c. 280 divided by c sigma c. Lever arm equation Z is equal to d minus x balance by 3. What is x balance? X balance is a neutral axis. So neutral axis equation is kd. So d minus kd by 3. So d is neglected and 1 minus k by 3. 1 minus k by 3. These are the lever arm Z equation. So I can call it Z into d. 1 minus k by 3 into d into is equal to jd. So j is equal to 1 minus k by 3. 1 minus k by 3. So these are the lever arm equation. Right now moment resistance. Moment resistance equation, total compression force into lever arm 1 to sigma cbc 1 half into sigma cbc b into x balance is equal to jd. So final equation is 1 half sigma cbc into kj into bd square. Okay, so here is the equation of moment resistance. So m balance is a qb square. So q is equal to 1 half sigma cbc kg, and q is equal to moment of resistance factor for a balanced section. Moment of resistance factor for a balanced section. And pt balance, percentage of steel. pt balance, percentage of steel, 100 q divided by sigma st into 1 minus k3. Okay, t balance, percentage of steel required, percentage of steel required for the balanced section design. Okay, tensile stresses in the member, so stresses is equal to ft divided by ac plus mst. This equation is from IS 456 2000, page number 80. 80 transform area of the section AC plus MAST AG minus AST MAST AG M minus 1 AST. Okay, these are the equation. 80 is our transform area of section. So area of compression plus M into area of tension here. So we just do simplify the equation. AG minus AST plus MAST, AG plus M minus 1 AST. So tensile stress equation FT AC plus M minus 1 AST. FT means T, area of concrete, plus M minus 1 AST. So FT is total tension member on the member. So right now we are going to design underground tank, underground water tank. Okay, underground water tank, we have a two shape here. First is rectangular and circular. Okay, so for the underground water tank we have earth pressure on the tank. Earth pressure on the tank, it's depend on the soil condition, dry or moisture, submerged black soil or backflip consist of C5 soil. So earth pressure on the tank wall is depend on the soil condition, or is earth pressure which varies triangularly along the depth of tank wall depend upon the condition of side fill. Okay, so in this case here is a water tank. Okay, here is a base and your earth pressure is in a triangular shape. Okay, earth pressure in the triangular shape. Okay, so here is a calculation of earth pressure at a base of tank wall for the dry and moist black fill. PA is equal to K gamma H. PA is equal to Ka gamma H. Okay, and here is a total pressure acting on the tank wall PA plus area of pressure triangle. Here is the pressure triangle. Okay, here is a PA, here is a height H. So pressure triangle area PA is equal to 1 half K gamma H square, 1 half into Ka gamma H square. So K is the coefficient of active pressure. So K is equal to 1 minus sin phi divided by 1 plus sin phi. Phi is angle of internal friction of soil. Phi is equal to angle of internal friction of soil. Look at here. Here is a tank wall, here is a earth pressure, triangular shape. PA is the center of gravity, at the center of gravity, CG. CG of the triangle shape, H by 3. So here is PA is different, here is PA is different. Okay, theory portion is completed and we are going to design a one water tank here. So first example of the water tank is so right now write down the first example. Design a rectangular underground tank for a capacity of 80,000 liters. Use M20 concrete and Fe415 grade steel. Take gamma saturated is equal to 80 kilonewton per meter cube. Gamma W 10 kilonewton per meter cube and phi is equal to 30 degree. So these are given. So this example, let's start. Okay, first of all we will consider the size of tank. So I am going to design a tank. Okay, so provide tank 6 meter by 4 meter by 3.5 meter. These are the assume. So I am going to assume the first tank dimension 6 by 4 by 3.5 meter. 6 by 4 by 3.5 meter. Okay. So right now we have to consider overall water depth. These are the overall tank design. Okay. Yeah. Okay. 3.5 meter height and 4 meter width and 6 meter is here. Okay. And right now we cannot fill the whole water tank, full water tank at a time. So we still need some freeboard. So water level is little bit nearer from the top of the slab. So I am provide freeboard 150 mm freeboard. So the water depth is 3.5 meter minus 0.150 meter. So water depth is 3.35 meter. Water depth 3.35 meter. Now let's check the volume. Volume 6 by 4 by 3.35. So volume is 80.40 meter cube. Okay. So these are the volume which we water stored in the tank. But here is one condition here. 1 meter cube is equal to 100 liters. 1 meter cube is equal to 100 liters. So 18.40 meter cube, 18.40 meter cube, as well as 80,400 liters capacity of tank. These are the capacity of tank. This is the capacity of tank. And how much we need? We need 18,000. We provide a more 400 meter. So our water tank dimension is complete. Okay. Now find out length by width ratio. Length by width ratio. So 6 by 4 is equal to 1.5 less than 2. Less than 2. So by this condition, if 1.5 is less than 2, at that time, a top portion of the wall, top portion of the wall, which one? Capital S minus small h. Capital H minus small h. This portion designed as a continuous frame. This portion designed as a continuous frame. So capital H is the overall depth. What is small h? Small h is equal to capital H by 3 or 1. Small h is equal to capital H by 4 or 1. So capital H by 4 1. 3.5 by 4. So its value is 0.875. Whichever is more we take as a cap. Small h, so small h is 1 meter. 1 meter. So we are going to design we separate a wall of water tank in a two part. First is capital H minus small h, and second one is 1 meter from the bottom. 1 meter from the bottom, and the 4 meter height, so is 3 meter, and here is 1 meter from the bottom, here is 3 meter. So here is the wall. Okay, overall height is 4 meter, and divide is here 1 meter and 3 meter, two parts. So is 3 meter, designed as a continuous plane, means it's designed as a simple wall. But this 1 meter is designed as a cantilever portion. This 1 meter designed as a cantilever portion, and 3 meter designed as a simple continuous flame. Okay, so right now we will start a design. So our tank is underground. Okay, tank is underground. Rectangular. Underground rectangular tank. Okay, so at that time, underground rectangular tank, we have a two condition. First is tank is empty. And surrounded soil is saturated. Surrounding soil is saturated. Okay, and the second condition, tank is full and no soil outside. Okay, So for the design of underground water tank, we have a two condition to describe here. So tank is empty and the second one is tank is full. At this both condition, there is force mechanism is changed. So by the first condition, tank is empty and surrounded soil is saturated. So our force is like this. Okay. For the tank is empty and surrounding soil is saturated. At that time, this type of means only soil force from the outside. But second case, tank is full and no soil outside. So at that time, water pressure is well outside. Okay. Now we have taken two conditions. Only one condition we are using for the design. The first condition is tank is empty. Tank is empty and surrounding soil is saturated. Tank is empty and surrounding soil is saturated. Now okay, so first condition we have a 3 meter is a continuous frame and 1 meter is a cantilever. Okay, by this we have to design a wall. Okay, so first we start for the 3 meter. Okay, so find out pressure at depth capital H minus small h. H depth capital H minus small h. Okay, so capital H minus small h, so capital H is 3.5, small h is 1, so 2.5 meter. Okay, so here is equation PA is equal to KA gamma dash into capital H minus small h plus gamma W capital H minus small h. Okay, so in this example we have a capital H minus small h, gamma W, gamma dash and Ka are missing. So let's find out Ka and gamma dash. So Ka equation is Ka is equal to 1 minus sine 30 divided by 1 plus sine 30. Okay, 1 minus sine phi divided by 1 plus sine phi. Phi is 30, so 1 minus sine 30 divided by 1 plus sine 30. So by this equation we have a K is 1 by 3. K is 1 by 3. So we will just gamma dash is missing, so gamma dash is equal to gamma saturated minus gamma W. So gamma saturated is given is 18 and gamma W is 10, so value is 8. So gamma dash is 8. Okay, so we have all the value here. Let's put all the value in this equation. So K is 1/3 into gamma dash is 8 into capital H minus small h is 2.5 plus gamma W is 10 and here is a 2.5. Okay, so here understand the equation. Okay, so first equation here is for the pressure of soil and second pressure of water. Okay, so what happened, soil is saturated, so soil and water both pressure is here, so as well as soil pressure as well as water pressure. So by this Pa is 31.67 kilonewton per meter square. So here is a pressure at 2.5 meter. Okay, here is a pressure at 2.5 meter. Okay, we are going to draw one figure. So this is the triangle. Note this here. Okay, this is a triangle. Okay, we find out 31.67 at 2.5 meter height. Here 2.5 meter. So at this point here is Pa is 31.67. 31.67, but this one is missing. So this one is missing. So we have to find out this value also. But right now we are going to design a 2.5 wall upper side, so we are going to design only this one, so we only need 31.67. okay, so let's start. First of all, we need a fixed end moments. Why? Here is a top view of the rectangular tank. Okay, this is 6 meter and here is a 4 meter. It's all joint. These are the joint here. Okay, so in the wall we have a movement, in the both we have movement, so is all are connected and behave like a continuous. Okay, first step, first describe with 2.5 meter wall is connected and behave like a continuous. So if I cut this from here and put it like this, so here is a support at the joint, here is also one support. So all this movement, here is a load is distributed in beam to beam, as well as is all movement is distributed in wall to wall. So we just need to distribute a moment. Okay, so first for the distributed moment we need a fixed end moment, FEM, fixed end moments, FEM. Okay, for the fixed end moment with a UDL load, fixed end moment for the UDL load plus design MFAB, okay, minus PL square divided by 12. So value is minus 31.67 into 6 whole square divided by 12. So value is minus 95.01 kilonewton into meter. Minus 95.01 kilonewton into meter, MFAB. Now MFAD plus PB square divided by 12. So value is 31.67 into 4 whole square divided by 12. So value is 42.22 kilonewton into meter. So here is a fixed end moment, both fixed end moment we find out. So right now we have the distribution factor, we need a distribution factor. Okay, At this time we did not calculate the whole fixed moment. What we did, here is a square, okay, A, B, C and D. We need only a one joint, okay. So at this joint we are going to design A to B and B to D, okay. And this design will exactly on CD and this design exactly on BC, okay. So we don't need the calculate the whole fixed moment for the all joint. We just need a one A joint and two sides, okay. So let's start our distribution factor. Moment distribution. So for the moment distribution factor we need a, so find out distribution factor via joint member stiffness summation of stiffness and distribution factor is equal to k divided by summation of k, okay. So first is joint A. Joint A. Member, we have a two member AB and AD. AB and AD. So stiffness K equation is 4 EI by L. K is 4 EI by L. So value is 4 EI by 6 and here is 4 EI by 4. Member AB length is 6 meter, member AD length is 4 meter, okay. So summation of K is 0.67 EI and 1 EI. So summation of K is 1.67 EI, okay. So right now we will find out the distribution factor for AB length. 0.67 divided by 1.6, 0.67 divided by 1.6, so distribution factor is 0.4. Second, for AD 1 divided by 0.6, so 0.6, distribution factor is 0.6, okay. Right now we are going to distribute a moment distribution at joint A by these two distribution factor. Moment distribution, okay. So first is joint D, joint A and joint B. First of all, write down the distribution factor DF. So DF is here, D is 0, B is 0. We will not find out here. So here is 0.6 for the AD and 0.4 for the AB. Okay, this we should find out. Second, we write down the FEM, fixed end moment. So fixed end moment D and B, we not find out the fixed end moment. We find out the AD fixed end moment 4222 minus 95.01 minus 95.01. Let's balance. Balance, okay. Balance, we have a 0 here to right test here. So balance the moment at joint A. These both are unbalanced moment. So right we balance. So difference between these two, 42.22 minus 95.01. 42.22 minus 95.01. Difference between these two multiply by 0.6 multiplied by 0.6 means a distribution factor. If this value is come in minus, we will write down opposite means plus 31.67. What happened here? Here, let's look at it. 42.22 minus 95.01. These are the difference multiplied by 0.6. So this value is minus 31.67. Minus 31.67. But we convert into plus and put it here. Okay. Same equation for this area. 42.22 minus 95.01 into 0.4. So value is minus 21.12. Convert it plus and write down 21.12. Okay. Next is final moment. Final moment. So how we find out the final moment? Simple. Summation between these two. 42.22 plus 31.67. This summation is 73.67. Second, minus 95.01 plus 21.12 equal to minus 73.89. So these are the final moment. These both are the final moment. So this final moment we can use for the design. Okay, this final moment at the joint, this moment at the joint. So this moment is used for the design of wall at the support. Okay, but we need a wall which is 4 meter and 6 meter. So we need a maximum bending moment. These are the 73.89. This moment kilonewton into meter. This moment at a support. At a support. But this moment are not a maximum. This moment is not a maximum. So what we need? We need a maximum bending moment. We need a maximum bending moment. At which portion we have a maximum bending moment? So maximum bending moment at the center. Maximum bending moment at the center of a long span. Of a long span AB. So maximum bending moment at the center of a long span AB. How we find out? PL square by 8 minus MA. PL square divide by 8 minus MA. So by this equation, PL is a force is 31.67. Length is 6 whole square divided by 8. MA means final moment 73.89. Okay, at the support. MA means moment at the support A, at a joint A. So at a joint A, moment is 73.89. So 68.62 kilonewton into meter. Okay. So these are the maximum moment at the long span. Right now, maximum bending moment at a center of short span. Which one? AD. Center short span PB square divided by 8 minus MA. So P is the same 31.67. Length is changed 4 whole square divided by 8 minus MA 73.89. So value is 31.66 minus 31.66 kilonewton into meter. Okay, these are the moment Okay, so we found out the best both moment. Right now we need a direct tension, we need a tension here. We have to calculate direct tension in long wall, direct tension in a long wall. So P into B by 2, P into B by 2, so value is 31.67 into 4 by 2. Here is a tension by a short wall. Okay, in the long wall tension is by a short wall, so divide B by 2. 31.67 value is 63.34 kilonewton into meter. Okay, same for the longest pump, sorry, shortest pump. Direct tension in a short wall, in a short wall, so P into L by 2, so P is equal to 31.67 into 6 by 2, so value is 95.01 kilonewton into meter. Okay, so our moment calculation is completed. So in the next lecture we will learn a design a reinforcement for the long wall as well as short wall. Okay.